It's just incredible how much transformers have completely, well, reshaped AI,
Oh,
right? From
absolutely.
understanding pretty much anything we write or say to getting, frankly, eerily good at seeing and generating images.
Mhm.
Their superpower is undeniably that attention mechanism, letting them weigh the importance of every other piece of information, no matter how far away, capturing those, global connections.
Totally. But there's this funny quirk, this sort of fundamental challenge at their core, that standard attention calculation doesn't actually know or care about the order or the position of the tokens.
Right.
Exactly. If you give a vanilla transformer, say dog bites man or man bites dog, the self-attention outputs for dog bites and man will be the same in both cases, assuming you start with the same token embeddings. It's like a bag of words, essentially.
Just a really sophisticated
A
one.
very sophisticated one. Yeah. But without adding something extra, it just has no inherent sense of structure, of sequence.
Right. And that's exactly why positional encodings became so essential so quickly.
Hmm.
The field has thrown, well, pretty much everything at this problem. You had the original sine and full sine waves, then just learning embeddings for each position.
And more recently, these clever relative methods like rope, rotary positional embeddings, that kind of bake the distance into the attention score itself.
Exactly. And while these methods definitely work, I mean, they're critical for how well transformers perform.
No question.
The underlying why can sometimes feel a bit like, well, black magic, can't it? And they all have trade offs.
That's true. Some don't extrapolate well if you suddenly give them sequences much longer than they trained on. Others might introduce weird numerical things. And, getting them to generalize perfectly across different kinds of data isn't always trivial.
So, okay, imagine this. What if you could design the attention mechanism itself from the ground up, not just adding positional info on top, but building it into the very core calculation using a completely different kind of math?
Hmm.
What if you thought about the sequence of tokens not living in flat, standard Euclidean space, but in a curved space?
Okay, yeah, that sounds wild. But, I mean, this is the kind of academic innovation that can genuinely shift paradigms. It's about bringing principles from differential geometry, the math of curved surfaces and spaces, right into the nuts and bolts of how these networks work.
And that is exactly what we're diving into today. Our source is this really fascinating recent paper called RiemannFormer, a framework for attention in curved spaces by Zhongping Ji. Plus, they included some really helpful supplementary notes that break down the concepts.
Yeah, those notes are useful. So our mission today is basically to guide you through the core innovations of this Riemann-Former framework.
Right. We want to help you understand this geometric interpretation of attention and see how it potentially pushes the boundaries of how we design these really powerful models.
Okay, let's unpack this core idea then. The paper starts by saying, forget thinking of token sequences as points lined up in flat, simple space. What if they're points living in a curved space? Why? Why even think about tokens in curved space? How does that help with attention?
Well, what's really fascinating here is how they reinterpret the whole problem of comparing tokens. Traditional self-attention uses a dot product between the query and key vectors.
Right, measuring alignment.
Exactly, measuring how aligned they are. But mathematically, taking a simple dot product like that implicitly assumes you're working in a flat Euclidean space, a space where you can just slide vectors around and compare them directly, no matter where they started. Think of it like using a ruler on a flat piece of paper. You can measure distance or compare directions anywhere on the paper in the exact same way. Okay, makes sense.
But now, think about a curved space like the surface of a sphere. The Earth's surface is the classic example. The whole concept of straight, how you measure angles, how you compare directions, it all changes depending on where you are as a sphere.
Mm.
The local flat approximations at each point, what mathematicians call tangent spaces, they're all different. They point in different directions relative to each other. So if you have a vector, like an arrow sitting at the North Pole, and another vector down at the equator, you can't just pick up the North Pole vector and directly lay it down next to the equator vector to compare their directions using a simple dot product. The geometry itself is different.
Right, because the ground under the vectors, so to speak, is curved.
Precisely. So the fundamental geometric challenge that Riemann-Former identifies is this. How do you perform a valid comparison, like an inner product or dot product, between vectors that essentially live in different local geometric environments within this overall curved space?
Okay, so if you can't just take the dot product directly between a query at one spot and a key at another, how do they compare them in this hypothetical curved space?
This is where a really key concept from differential geometry comes in. Parallel transport.
Okay.
Imagine you have that arrow at the North Pole, and you want to move it down to the equator. Parallel transport is the process of sliding that vector along a path on the curved surface in a way that keeps it pointing straight relative to the surface as you go. It's a way to move a vector along a curve in curved space such that it stays as consistent as possible with the local geometry it's passing through.
Okay.
Now, in RiemannFormer, they don't explicitly define the whole curved space itself, or like the specific coordinates of the tokens within that space. That would be incredibly complicated. Instead, they learn linear mappings, or transformations, that effectively act like this parallel transport.
Ah, they learn the transport itself.
Exactly. So before taking the inner product of a query vector qm from position m and a key vector net from position n, they use these learned transformations to essentially transport the key vector net into the local geometric space, the tangent space of the query vector qm. Only then, when both vectors are effectively sitting in the same local neighborhood, mathematically speaking, do they take the inner product.
I see.
The attention score calculation essentially becomes this kind of geometrically corrected inner product. It's a major departure from standard attention.
Okay, so the idea is to transport one vector into the other's local space before comparing. That makes conceptual sense, definitely. How on earth do you make something like parallel transport and curved space geometry learnable within a standard neural network using just, weights and biases? That sounds like heavy math.
It does, and that's really the ingenious part of the paper. While the underlying concepts are complex, they use what the paper calls these ingenious predefined configurations to drastically simplify the mathematical components that actually need to be learned. Okay. The key components relate to, one, the local geometry at each point described by something called a metric tensor, and two, the transformations that perform this parallel transport between points.
Right.
So instead of trying to learn some incredibly complex, high-dimensional mathematical object for the metric tensor at every single position, they constrain it. They preset it to have a very simple, low-parameter form. Often it's just a simple diagonal matrix, or even simpler, just a single scalar value, like a scaling factor S, that scales everything locally.
Just one number.
Sometimes, yeah. They note this corresponds to a conformal deformation, basically stretching or shrinking space equally in all directions at that point. But the point is, the model just has to learn this one scalar S for each position, maybe constrained in a certain way instead of a whole matrix. That dramatically cuts down the parameters.
Okay, that simplifies the local geometry part. What about the transport, the transformations between positions?
Similar idea. Those transformations that act like parallel transport, aligning vectors from different spots, they're also simplified. They decompose them into a scaling part, which is related to that scalar S we just talked about, and a part that preserves lengths and angles locally. And this length preserving part is implemented using very simple, learnable building blocks. Think blocks of 2D rotation matrices or sometimes reflection matrices arranged in a block diagonal structure.
So like rotating pairs of dimensions.
Exactly. Instead of learning a full complex transformation matrix for moving between any two positions, the model might just need to learn a few rotation angles, theta, that define these simple rotations or reflections.
Ah, okay.
And the real magic, or the ingenious configuration, is that they predefine the mathematical structure of these simplified metrics and transformations, like rotations based on theta, such that they automatically satisfy a specific mathematical relationship. This relationship ensures they are consistent with some underlying, albeit unspecified, curved geometry. It guides the learning process to find parameters in theta that make geometric sense, but using far, far fewer parameters than trying to learn the geometry from scratch.
Okay, wow. So by learning these simplified components, like a single scaling factors for the local space and maybe a few rotation angles theta for the transformations between spaces, how does the model actually figure out where the tokens are in the sequence? Does it still need those traditional positional encoding vectors added to the input tokens?
No, and this is a really key claim of the framework. The paper explicitly states it obviates the need for explicit positional information in the traditional sense.
So no adding sine waves or learned vectors.
Correct. The positional information isn't added externally anymore. It's implicitly captured within the parameters of the learned geometric structure itself, within those learned S and theta values.
How does that work? How does learning and theta tell it about position M and position N?
Well, if you connect this back to the attention calculation, when you actually work through the math of that geometrically corrected inner product, using those simplified learned scaling factors and rotation angles, theta derived from distance, terms naturally pop out that depend directly on the positions M query and N key.
Ah,
Specifically, you get terms in the final attention score formula that involves S raised to a power related to the sum of the positions, M plus N, and you get other terms that involve rotations or reflections based on the difference of the positions mn.
So m plus n gives absolute position info, and mn gives relative distance.
Precisely. If that scaling factor s is learned to be anything other than 1, then the etsum plus n2 term means the attention score explicitly depends on the absolute positions. The rotation part, involving mn theta, naturally depends on the relative distance. So the model learns parameters that inherently encode both absolute and relative positional information just by figuring out the optimal geometric relationships between tokens for the task.
That's really neat.
And what's fascinating here is that the model isn't forced to use the absolute position information if it's not helpful. The paper notes the model can, and I quote, autonomously emphasize the relative information during the learning process by adjusting the parameters.
How so?
Well, think about it. What happens if the model learns that the best value for s is exactly 1?
If s is 1, then s to the power of anything is still 1, so that sm plus n2 term just becomes 1. It vanishes.
Exactly. If s equals 1, the part of the attention score that depends on the absolute positions, m plus n, just disappears entirely. And the remaining part, the part involving rotations based on the relative distance, mn, looks remarkably familiar.
Where is this going? This leads to that cool connection you mentioned earlier, doesn't it?
Absolutely. This raises a really important observation. If s is learned to be exactly 1 across all positions, the resulting attention formula, derived purely from this curved space perspective, mathematically reduces to having the exact same structure as rotary positional embeddings, rope.
No way.
Yes, it's a really significant insight. It means rope, which is this very successful and widely used method specifically designed to inject relative positional information using rotations.
It can actually be seen as just a special case of this more general RiemannFormer framework.
That's exactly what they propose. RiemannFormer essentially provides the model with the flexibility. It can learn if absolute position information is useful, by learning is different from 1, or if only relative position matters, by learning SEOs 1, which effectively recovers rope's behavior. It suggests there might be a deeper geometric reason why rope works so well.
Wow, okay, that's a powerful unification, seeing a popular method fall out as a special case. So this geometric approach handles positional encoding implicitly, capturing both absolute and relative info. But the paper also introduces this other mechanism called locality focusing. What problem is that one solving? Why is it needed on top of the geometric stuff?
Right, good question. Because even if you have perfect positional information, vanilla transformers still have this known Achilles heel. They lack a strong local inductive bias.
Meaning they don't inherently prefer nearby information.
Exactly. Think about traditional computer vision using convolutional neural networks, CNNs. They use these small filters, these kernels, that are forced to look at tiny neighborhoods of pixels first. They build up understanding starting from very local patterns.
Mm.
Transformers, on the other hand, calculate a tension between every pair of tokens right from the get-go. Globality is their strength, which is amazing for finding distant connections, but it means they don't have that built-in preference for local relationships the CNNs have.
And that makes them data hungry.
That's a big part of it, yeah. They often need huge data sets to learn even simple local patterns that a CNN would pick up much more naturally and efficiently. So locality focusing is an explicit mechanism introduced in RiemannFormer, specifically designed to tackle this issue. It's a separate step added after the main geometric attention calculation is done.
Okay, so how does it work?
It introduces a learned decay factor, or a penalty, based purely on the distance between tokens in the sequence or on the grid. This decay factor is then applied to the values, the V in QKV attention, that are being aggregated by the attention mechanism.
Ah, it modifies the values, not the attention scores themselves.
Primarily, yes. The idea is, even if two tokens have a high attention score because their query and key vectors align well geometrically, if they are physically far apart in the input sequence or image, the locality focusing mechanism will dampen or attenuate the contribution of the distant token's value when creating the output for the current token.
So it's like saying you seem relevant, high attention score, but you're far away, so I'll listen to you less.
That's a great way to put it. You can visualize it like a sophisticated filter, maybe like a bilateral filter from image processing. The geometric attention determines similarity or relevance. Locality focusing then weighs the contribution based on proximity. By applying this decay, softmax, or KAODK, where click contains the decay, to the values based on distance, the model is explicitly encouraged, nudged, to prioritize information from nearby tokens. It injects that missing local inductive bias.
Okay, that makes sense. So we have the geometric part handling position implicitly and locality focusing explicitly promoting equal interactions. So how did these two innovations actually perform when they put them to the test in the paper?
Right, the results, they primarily validated RiemannFormer on image classification tasks, and importantly, they focused specifically on using small data sets, namely CFAR 10 and CFAR 100. They used a relatively lightweight vision transformer, or VAT, architecture for these tests.
Which is a good test bed, right? Small data sets often really benefit from stronger inductive biases like locality.
Exactly, that's where you'd hope to see the difference. And the results they present in their Table 1 are quite compelling. RiemannFormer, just using its geometric positional encoding on its own, consistently outperformed the traditional methods they compared against things like using no positional encoding at all, using standard sinusoidal embeddings.
And rope?
And notably, it also beat rope on both of these data sets in their experiments. For instance, on CFAR 100, which is generally harder because it has more classes and fewer images per class, RiemannFormer alone achieved a noticeably higher accuracy than rope did.
Okay, so the geometric part holds its own. What about locality focusing?
Yeah, this is where it gets particularly striking. Locality focusing used by itself without RiemannFormer's geometric encoding didn't actually perform very well.
Which makes sense. You said it's not really a positional encoder.
Right, it's more of a local attention modifier, and this is the key finding when they combined RiemannFormer with locality focusing, denoted as RiemannFormer plus LF, the performance jumped significantly higher again. It achieved the best scores on both CIFAR 10 and CIFAR 100, substantially outperforming RiemannFormer alone and all the other baselines.
Ah, so they really complement each other.
Strongly, yes. It really supports their hypothesis. The geometric approach provides a powerful implicit way to understand and encode position, maybe balancing absolute and relative info. And then locality focusing provides that crucial explicit local bias that standard transformers often lack, leading to much better performance, particularly on tasks where local features are important and critically where data is limited. They specifically note the greater enhancement on CFAR 100, which fits that low data scenario perfectly.
This is genuinely fascinating work. It feels like a really different way of thinking. What does it suggest for the future of transformer design? Where could this, geometric way of thinking take us?
Well, the paper itself presents this as a preliminary validation, so they're careful not to overclaim, but the implications could be pretty significant. If we try to connect this to the bigger picture, it really suggests that thinking about the inherent geometry of the data itself, whether it's a sequence of words, a grid of pixels, maybe even graph data, might be a powerful new paradigm for designing neural network components, moving beyond just treating everything as vectors interacting in a default flat space.
Mm,
For future work, they clearly plan to test this framework on more visual models and, very importantly, on large language models to see how well these ideas generalize to different kinds of data and at much larger scales.
that'll be key.
Definitely. The paper also candidly points out that even with this elegant geometric interpretation, the exact mechanistic role of the positional information learned this way isn't fully understood yet. Like, how exactly does the network leverage the S and theta parameters? That offers a really deep, exciting avenue for future theoretical work. And of course, exploring different simplified geometric configurations, maybe different angle schedules for those rotations, are also mentioned as key next steps.
So it opens up a lot of questions still.
For sure. But it positions RiemannFormer not just as, another trick for positional encoding, but potentially as a more general framework, one that tries to bring together fundamental geometric principles with the power attention. And by learning aspects of the data's underlying curved space, perhaps, and adding targeted mechanisms like locality focusing, it offers a new path toward building models that can potentially get better at capturing both global relationships, which is Transformers' traditional strength, and those essential local patterns. And that can be especially valuable whenever you don't have a Mount Everest of data to train on.
Okay, so let's recap. We've taken quite a deep dive into RiemannFormer today. We've explored this really innovative idea of treating attention as a process happening in a curved space,
Hmm.
simplified into learnable components like local scaling and rotations data, using those ingenious predefined configurations. We saw how this geometric approach seems to implicitly capture both absolute and relative position.
And has that remarkable property of potentially encompassing rope as a specific instance just by learning S1.
Right. And then we looked at how adding that separate locality focusing mechanism provides that crucial local inductive bias, explicitly encouraging attention to nearby tokens, which really boosted performance, especially on the smaller data sets they tested.
It definitely gives you a new lens, a new perspective maybe, on what could be happening inside those attention layers or what could be happening.
So, what does this all mean for you listening in? If moving our thinking about data, just shifting the assumed geometry from flat space to curved space, and learning these subtle geometric structures can unlock new potential and improve performance, particularly when data is scarce. Well, it leaves us wondering, where else might applying principles from differential geometry or perhaps other advanced mathematical fields reshape how we design and understand these incredibly complex neural networks?
Hmm.
It really prompts us to consider the potential hidden geometries that might exist within the vast and complex data we feed our models every day. And maybe, just maybe, how much more performance and insight is still waiting to be discovered by exploring those deeper mathematics.